Hello and welcome back to the Calculus Fun Room. In this video I want to discuss with you the topic of work. So when we discuss work, the idea we're discussing basically is the amount of energy that we would expend through some activity. So I just went on YouTube real quick and pulled up a short video of an animation. And if I think about the amount of energy I would expend or amount of work that I would do in pushing a box, so say I have a box that sits still and I push that box across the floor. Now the amount of force that I exert, right, how hard I push, is going to determine how much energy I expend, and the distance that I push the box is also going to be variable of how much energy I expend. Right? The further that I push the box, the more energy, and the stronger the force that I push on, the more energy I will expend as well. Now if we stop and we kind of rewind this animation, right, the amount of energy I expend is kind of, let's say, for like every second that I move. Let's look at the time variable for a moment. So if I push for 1 second, there's a certain amount of energy, and then if I push from 2 to 3 seconds, there's an amount of energy. If I push from 5 to 6 seconds, there's an amount of energy. So I have this summing process ultimately that I'm going to want to do here. But in essence, the general definition is that the work that I do will be dependent upon the force that I exert and the distance that I move. So a definition that we might see here is that work equals the force, let's say, times the distance. And symbolically, we usually will write that as W equals F times D. Now in this animation is a little bit more complex, sophisticated than we want to deal with here initially in this section of a calculus textbook. What I mean by that is when we're considering the forces within this system, we have the force of gravity that's pulling the box down to the ground. We have the force that I'm exerting on the box pushing. We have a friction force as well. So the force that I have to push with has to overcome the pull of gravity, i.e. the weight of the box, and the friction force on the floor. Now within a course of this nature, we aren't going to consider friction, so we're going to for the most part be lifting objects straight off the ground, so that the only force that we're fighting is the force due to gravity, the weight of the box. So if we're dealing with metric units, let me switch colors here. If we think about metric units, we would in essence be looking at the force due to gravity, lifting straight up and down. And Newton's law of motion says that force is mass times acceleration. So within the metric unit, the mass we typically measure with kilograms, and acceleration is meters per second squared. So these would be the units of force, and we call this a Newton. So we use the uppercase N, right, and this is a Newton of force. So just scroll down a hair here, and so to continue with this conversation just about units, so within the metric system, again, I'm looking now at work is force times distance. Right? So we're talking about the force being newtons, and our distance we're going to measure in meters. Right? Our acceleration was meters per second squared, so our distance is also in meters, and we typically call this a joule. And we denote with a capital J. So a joule is a measurement of energy, and we're not going to call it energy in this course. We're going to call it work. Now, if we're looking at the U.S. customary units, let me switch colors here. A force, again, if we're just fighting the force of gravity, that is our weight. So in the U.S. customary units, our weight is the force. So our force is measured in, I'm going to say pounds. That's typically how we measure the force, P-O-U-N-D-S, right, which we abbreviate as L-B. Now, when we talk about distance for the U.S. customary units, right, we talk about feet in that situation. That's our unit that we look at. So our force times distance is going to be our pounds times the feet the units that I travel. Now again, the reason we're using feet is because technically 9.8 meters per second squared is the force of gravity in metric units, and then so feet per second squared is our measurement of the acceleration of gravity in the US customary unit. So we're using feet as our distant measurement here, and we typically denote this as foot-pounds for work or energy, right? We're going to call work in this section. All right, so let's take a look at a couple examples. And again, we don't want to introduce friction into our systems of motion here. We're just going to be lifting objects straight up and down so that we're only fighting the force of gravity. So in this first example, let's ask how much work is done. Let's say we're lifting a 20-pound box. And let's say we're lifting that 6 feet off the ground. Right? So how much work is done in that motion? Right? So again, we know that work is the product of force times distance. So for this problem, because we're in US customary units, the force is the weight of our object. So we have the 20-pound object, that is our force, and we're fighting gravity. All right, so again, gravity is measured within that force, that weight, and then the distance that we're moving is 6 feet. So in total, the work we would do in that movement, let's see, 6 times 2 is 12. So I'd have 120 foot-pounds of work that I would do through lifting the box, 20-pound box, 6 feet off the ground. All right, now let's look at an example with metric units. So in this example, let's ask the same type of question, right? How much work is done lifting, let's say we have a 1.2 kilogram book, and we're going to lift the book 0.7 meters off the ground. Okay. I can't spell today. Ground. So how much work is done lifting 1.2 kilogram book off the ground? So again, we have our formula that work is force times distance. Now the issue here initially is that the force is a weight, and the weight in the metric system of kilograms, right, doesn't really involve the force. We have to evaluate the Newton's second law of motion, that force is mass times acceleration. So for this problem, our mass is 1.2 kilograms, and we have 9.8 meters per second squared as our acceleration due to gravity. So if I multiply those two together, I get 11.76 newtons of force. So let me change colors again. We're going to come back to our work formula. So the work is involving a force, 11.76 newtons. And the distance that we're going to move is 0.7 meters. And again, the distance needs to be meters because that matches our meters per second squared unit there. If I multiply these two together, I get 8.2 joules of work to move the 1.2 kilogram book 0.7 meters. Now, in both of these situations that we looked at here, our assumption was that the force was constant. Now, if we think back to, let's say, pushing that box animation, let's say that I start pushing slow, and I push harder and harder and harder, and I end up, almost, let's say, running behind the box. So the force that I apply is variable. It's changing throughout my motion, the length or the distance that I push the box. Now, to visualize this in a little bit more of a simple way, right? I'm going to ignore friction, right? But I'm going to suppose that, let me change colors. I'm going to suppose, let's say I have a box here at the origin, and I'm going to push that box, let's say, to this point here. So let's say this is some distance of x. Right? So the distance could be 5 or 7 or 10. Now let's suppose that at the beginning of my pushing of the box, I'm pushing very lightly, just enough to get the box moving, and then I start pushing harder and harder and harder and harder as I move along. So my force is variable, if you will. So how am I going to determine the work done when the force is variable and not constant? Well, I mean, in essence, I'm going to do the same thing that I have done throughout a lot of the conversations in a calculus course. We're going to estimate the work by chopping, if you will, this distance that we moved into small units. And we're going to estimate the work done. So for example, let's say I look from, this position to this position. Well, if this is a relatively small distance between, let's say 0 feet and 1 feet, right, the force is going to stay relatively constant. Right now, way out here, my force might be much stronger than it was back here in the beginning. But if I make these two cuts really close to each other, we could think of the force as roughly constant here. So in this segment that I'm highlighting, there's a roughly constant force, and the distance that we traveled was some delta x, the distance between those two. And I would continue this process, right? Then I would look from, let's say, 1 foot to 2 foot. And again, in that particular segment, the force is roughly constant. So in this segment here, the work is roughly a constant force times the distance moved. Let's call that the work of the first segment that I'm looking at. There's the first delta x. And then the the distance moved between the next two. Right? I'm going to have the work done in segment 2 being the relatively constant force times the distance moved in that interval. And ... So we're going to have, let's say, the ith interval here. So I have some distance between I minus 1 and I. And then the force, again, if this is small enough, the force is roughly constant. So the work in the ith interval is the roughly constant force times the distance in that ith interval. Now again, typical process in calculus, we're going to say the total work, right? So the total work is going to be the sum of all of those individual pieces of work for the n segments that we cut this into. So just like with area under the curve, we use n rectangles. Now the total work is approximately that value. Let me switch that symbol. Right? And let me scroll just a little bit here. Oops, where are you going? All right, so my exact work, let's say, here's my total work in an exact manner, right? It is going to be, and let me leave a little bit of room here, it is going to be the sum of all of these little works. And remember, all of these little works are the forces. Now remember, the force technically is a function of the distance that I moved. So I'm going to say f of x, right? So if I come back up to my figure here, let me scroll up a second. In this really tiny slice of distance, we said the force was roughly constant. And then out here in this tiny slice, it was roughly constant. Now if I start off slow and I push harder and harder and harder to where I'm running by this end of my motion, the force is changing. So the force might be pretty small here, but it's going to be pretty large here, and it's a function of the location x that I'm at, right? So again, if I'm at, x equals 1, my force is kind of small in relation to out here at x equals, let's say, 10. So the force is a function of my x location. Let me say at my x location, and then times the delta x at that particular location. Now again, the sum of the n segments of work is an approximation, but when I take a limit as n goes to infinity, that's going to give me the exact measurement of the work. Now this is the limit of a Riemann sum, so I'm going to end up with the integral of my variable force function, and technically we would be going from point A to point B. Right, whatever those limits of integration might be. So a formula for work when I have a variable force function would be described by this integral formula. right? And then a reminder of the big picture of this chapter that we're discussing is applications of integration. So this is one of the applications of integration where we have a variable force and we're summing up all of the forces over the interval of distance that we moved. All right, now a really classic example of a variable force involves Hooke's law in a spring. So let's say I have a frictionless floor here and I have a wall here, and let me change colors, and let's say we've fastened to this wall a spring. So let's say our spring has some kind of natural length, and let's say we have a box attached to that spring. So we have some type of mass, let's say, on that spring. So let's say this is the equilibrium position, if you will. Right? So this is the, let's say, no stretch or compression on that spring. I haven't moved the spring anywhere, and there's no force being applied. Now, if I push in on this box, I'm going to try to redraw this here and make it a little smaller. If I push in on this box, what's happening is I'm compressing the spring. So the spring is going to compress. And if you think about, springs, as I push on the spring, it's going to push back. It wants to come back to equilibrium. So as I push, it has a restoring force, if you will. I push, and it wants to push back on me. So as I compress the spring, the force pushing back on me is increasing. If I only push the spring a small amount, the force isn't as strong. If I push the spring in very far, the spring is pushing really hard. So the force of the spring is varying over the distance that I compress the spring. And this is also true for, let's say, stretching the spring. See if I can scroll a little bit here without the digital board getting wonky on me. Right? So if I think back to my let me say, here was my equilibrium position here. If I think back to my equilibrium position, but this time I stretch the spring, right? So I'm going to stretch the spring. Now the property of a spring, that's not a very good spring. The property of the spring, again, is that it wants to go back to its equilibrium position. So as I pull the spring, it's going to want to pull back on me. It wants to come back to its equilibrium position here. Now again, just like with compression, as I pull on the spring, the small distance that I move, it only pulls on me a small amount. The further that I stretch that spring, the stronger, right, the force increases. So this is a variable force that we're dealing with here. Now, Hooke's law says that the force that a spring exerts is proportional to the displacement of the spring. Now what we'll do in this course is we'll use the letter X to represent the displacement because we're thinking, on a horizontal x-axis here. We've displaced in this x direction or this x direction. So the force is proportional, and the K value is the constant of proportionality. That K value is going to change. It's going to vary based on the type of spring. We could have a spring that's like a slinky. I don't know if you remember the toy of a slinky. The material the slinky is made out of is pretty thin. It's usually a plastic or a thin metal. So when I pull on that spring, that slinky, it doesn't pull very hard back on me. If I think of a spring like a shock absorber on a car, that's a pretty thick spring. It's made of strong materials. Shocks on airplanes when they land, those have to be real thick and rigid and sturdy. It takes a lot more energy to compress a spring of a car shock absorber than a slinky. So this K value, this constant of proportionality, is going to vary depending on the type of spring and the materials that are used to make the spring. All right, so let's look at an example of a spring situation where we're going to have a variable force here. So let's say in this example we have a force of 40 newtons is required to hold a spring. So we're going to pull the spring instead of compress. Right? A force of 40 newtons is required to hold a spring of 10 centimeters to a length of 15 centimeters. So the question we're going to ask is how much work how much work is done stretching the spring, let's say from 15 centimeters to 18 centimeters. Question mark. All right, so in this situation, and I'm going to draw in a horizontal manner, have a spring that is 10 centimeters long. Now, just like I drew in the picture above, I'm going to think of the natural length of the spring as really being x equals 0. So I haven't displaced the spring in any way, shape, or form. Now, in this situation, what I'm doing is I'm pulling the spring from 10 centimeters to 15 centimeters. So let me change colors. I'm taking the spring, which is a length of 10, and I'm coming out to 15 centimeters. So it's really a displacement from 10 length to 15. It's a displacement of 5 centimeters. Right? So, and the reason that we make that distinction is Hooke's law, when we wrote F equals K times S, the S represents the displacement of the spring from equilibrium. So when I write F equals K times X, this X is really representing the displacement of the spring from equilibrium. Now we are told that the force in this situation was 40 newtons, and the displacement is 5 centimeters. Now remember, the displacement has to be meters in these units of metric. So I'm going to say this is what, 0.05 meters. So the K value, the constant of proportionality for this spring, is going to be the 0.05 newtons, excuse me, the 40 newtons divided by 0.05 meters, and that's going to give me my constant of proportionality, which would be 800 for this particular spring. So what we have in this case is we've built our force function, right? So if this is my force function, we just found out the constant of proportionality is 800. So our variable force function is described as F equals 800 times X. All right, wanted to scroll down just a second here. And the question is saying how much work is done. Let me change colors to gray. How much work is done in moving the spring from 15 centimeters to 18 centimeters? Now again, remember this X measurement is a displacement. So we're technically going from a displacement of 5 centimeters to a displacement of 8. So we're really going from a displacement of 0.05 meters to a displacement of 0.08 meters. So again, we had 10 centimeters as our original length. We're going from 15 to 18, so that's a displacement of 0.05 to 0.08. So when we do our integral here, we're going to be summing up from 0.05 meters to 0.08 meters the work of my force function, so F times dx. So my force function is F, and then the dx represents the distance over the interval of 0.05 to 0.08. So there's the concept of work with a variable force in an application of a spring involving Hooke's law for the constant of proportionality of the spring. So then to finish this integral, this really goes back to a Calc 1 problem, right? I'm going to pull the 800 out as a constant. The integral of x is 1/2 x squared, and then I'm going to evaluate from 0.05 meters to 0.08 meters. So scrolling a little bit more, and I'm going to plug in the upper limit. So I'm going to have 0.08 squared over 2, and then minus the 0.05 squared over 2. Right. Taking out my calculator, I get 1.56, and our work unit is joules within our metric system. Okay, to save a little bit of time, I did a copy-paste problem out of Stewart's textbook. So what I want you to do for me is I want you to pause the video. I want you to take a look at this problem and solve this problem on your own, very similar to what we did in the prior problem. My hint to you here is even though in this problem you're compressing the spring instead of stretching, that doesn't change anything in regards to the compression. So all of the distances here will be positive, even though we're making the spring shorter. All of the work, all of the force is calculated through positive distance, positive compression. So pause the video, attempt this problem, and when you're done, unpause, and we'll do this together. All right, now that you've unpaused the video, how'd you do? All right, sounds good. Let's take a look at this together, and let's check your work. So again, I'm going to visualize the situation. I'm such a visual learner. So here's my scenario here, and I have a spring that has a natural length of 40 centimeters. So you want to say we're somewhere around here. Now remember, we want this to be in meters, so I'm going to go ahead and convert to 0.4 meters. So this situation is saying that we need a force of 60 newtons to keep the spring compressed 10 centimeters. So if I'm moving to 10 centimeters, I'm technically moving to 30 in length, but the displacement here is 10 centimeters. So I have 0.1 meters of displacement. Right? Keep in mind, these are all positive measurements because they're displacement distances. So even though technically we were thinking of this as like x equals 0, it's not. It is really just a equilibrium position, and the displacement is 10 centimeters. So what that would allow us to do, let me come over here and scribble the work. We have force equals k times x. Right? Hooke's law says the force is proportional to the distance. So in this case, the force was 40 newtons. Excuse me, the force was 60 newtons. We don't know the spring constant, that's what we're finding, and our displacement was 0.1 meters. So we would have the 60 newtons divided by the 0.1 meters gives me our spring constant, and that would be 600. So we have our force equation, right? So our force equation here, for this particular spring, the force is variable with a spring constant of 600. Right, now the first question being asked was how much work is required to compress the spring. Oh no, that's not the first question. The first question, let me change to a different color, is how much work is done during this compression. So the compression, right, we're going in essence from a compression of 0 to a compression of 0.1 meters. So the work done is over the interval of 0 to 0.1 meters for our spring with variable force spring constant of 600. All right, so this really is the concept here. Here's the setup of the integral. If I were to continue working this integral out, right, I'm going to pull the constant of 600 out. I have 1/2 x squared is the antiderivative of x, and then I'm going from 0 to 0.1. So I'm going to have, half of 600 is 300, and then I'm going to have 0.1 squared, and then minus 0 squared, which obviously 0 squared is 0. And then this becomes 3. Whoa, what kind of 3 was that? Let me grab my digital eraser. So this is going to become 3 joules as the work to complete that compression. All right, now the second question that I highlighted in green said how much work is required to compress the spring to a length of 25 centimeters. So if I come back to this visualization here, let me pick a different color of green. So we're compressing to a length of 25. So we're going from 40 centimeters and we're going to a length of 25 centimeters. Now obviously that is a distance of 15 centimeters. So we're going from 0 of natural length to a 15 centimeter or 0.15 meter compression. So let me scroll down here. We're integrating from 0 to 0.15. Come on, board. Please cooperate. There we go. So we are calculating the work from natural length to 25 centimeters long. So there was a compression of 15, and 600x is our variable force. So if I work this out, this turns out to be 6.75 joules of work to complete that compression. The next type of example we're going to look at comes from lifting objects similar to the box. We're lifting objects in a vertical manner. But again, the box was a constant force. We're going to look at something where the weight of the object changes, right, which really changes the force. So kind of a classic example here would look something like this. Let's say we have a 200-pound chain, let's say. That is 100 foot long and hangs vertically. Hangs vertically from the top of a building. All right. So the question we want to ask here is, let's say, and actually I wouldn't do two parts here. So first of all, let me kind of draw this picture. Let's have a little bit of a conversation, and then we're going to have a part A and a part B. Now, for simplicity in a visual manner in setting up our axis, if I think of, let's say here's the ground and I have my building here. To make things as simple as possible on me in regards to setup, I'm going to think of this as 0, right? So if my chain is hanging, let's say this is 100 feet, right, of chain long. Here's the position 0 of chain. So we're going to set up our x-axis kind of upside down. This is interesting how we do this. So we're going to look at like the ith segment of the chain. And in fact, I'm going to look at this tiny little piece of chain. Now, first of all, what I need to do is determine what the force is of the entire chain that is hanging here. Now, in particular, what I really want to do is look at what each segment weighs in particular. Right, and we know the entire cable weighs 200 pounds. So we know the entire weight of the cable is 200 pounds, and we know the cable is 100 feet long. So what that tells us in kind of a density manner is that we have 2 pounds per each foot of chain that we're dealing with here. So the whole chain being 200 pounds over 100 foot length, we have 2 pounds of weight per foot, right? Assuming that this chain is equal density, right? Same type of material all the way through. Now, if I cut this chain into segments, let's say this segment of chain that I cut here is 1 foot. So if I have 1 foot of chain, this chunk of chain weighs 2 pounds. If what I cut here is, 5 feet, then I have 2 pounds for each of 5 feet. So I'm going to have 10 pounds of chain there. Now, in general, I don't want to prescribe a specific piece of length of chain I'm cutting. I want it to be any length of cut, right? So if delta x is the length of the chain, then the weight, right, or the force, if you will, of that particular chunk of chain, right, the force of that chunk of chain is going to be the 2 pounds per feet times the delta x feet length of chain that I have. Now, if I look at this one particular chunk that I cut here, if I'm lifting this entire chain to the top of the building, right, that's what we're going to propose here. So we're going to pull this chain to the top of the building. This particular segment is going to move this distance. Right? Let me highlight in green. So this is the distance that this chunk of chain will move. So again, if this position is at 50 feet, since my chain is 100, this chunk of chain will move 50 feet up until it's at the top of the building. If this chunk of chain was at the 80-foot mark, then this distance, this chunk of chain is going to move 80 feet. So if I'm picking any arbitrary x location, this chunk of chain at the x location is going to move a distance of x sub I feet. So if I'm thinking of, and I don't want to write that there, right? If I'm thinking of work, right, work is force times distance. Right? So let me go back to blue. My work is going to be the force times the distance moved. So we have the force being 2 times delta x, and we have the distance that moves is x sub I, right? The location of that particular piece of chain that we cut. All right, now as we move this entire chain up to the top of the building, we're summing up all of those little pieces of work, right? So I'm going to write this out, but I'm going to be a little lazy with this, right? So the work of the entire chain is approximately the sum of all of those little pieces of work, right? So we have all of our forces times our distances moved, right? We technically cut that chain into n segments. So the total work of all of the chain is the limit as n goes to infinity of all those pieces of chain. So I'm just going to rewrite this, right? This is 2 times the x times the delta x, and there's our integral. So we have the limit of the Riemann sum, so we're going to get 2x dx. And you know, if the length of my chain is 100 feet, this is going to be 0 to 100, and I'll propose that question in just a second. Now, why is this a variable force? So let's think about this physically for a moment. So initially, I'm a little dude. I'm going to draw a stick figure up here. All right, so here's my arms. Now probably I need both arms reaching the chain. Okay, so as I'm pulling the chain, I'm placing the chain behind me. So as I pull up, let me switch to gray. As I pull a segment of chain up, the chain is now gathering behind me. And I have less chain below me. So again, let's suppose I pull up 1 foot of chain. I am now only holding 99 feet of chain. And so that's less weight. Right? So I now have 2 pounds per foot times the 99 feet left. A little bit less weight, right? If I pull up 30 feet of chain, I now have 30 feet behind me that I'm no longer holding. I have 70 feet now that I'm supporting. Chain is getting lighter as I pull it up. So this is a variable force that I'm having to deal with. The force, the weight of the chain, is lessening in a variable manner depending on the distance that I have moved it. And that's why we get this variable equation here. So the variation of the force comes really from what we could call the linear density. You won't see that term used in this section, but we're really going to look at how much weight per unit length. We're going to look at the density, and that calculation of our linear density is going to provide really kind of like that constant of proportionality like we had with Hooke's law. All right, so I've been having kind of a physical conversation with you without doing a whole lot of calculus that we've been kind of focusing on the work. So I told you I was going to ask a part A and a part B. So let's say part A of my question here is how much work is done lifting the entire chain, right? Lifting the entire chain to the top of the building. So that's a question. I'm going to put a question mark. So I'm going to scroll back up on my picture real quick. Right? So if we're looking at how much the chain is moved, right? Every segment that I slice here, this segment here, this segment here, this segment here, all of those segments move from 100 up to the 0. So we're really moving the chain from my position of 0 to 100. We're moving all of the chain along that distance. So my limits of integration, I'm going to have my integral that I have here. I have the integral of the 2 pounds per feet times the distance that I moved. And I'm going to look at the entire length of that piece of chain. So I'm going to skip the work of doing this antiderivative. Right? There's the concept of this chain idea, moving a weight that is a variable weight, unlike the box in the very beginning. So if I crunch out this integral, I'm going to get 10,000 foot-pounds of work necessary to move that entire chain. So I told you I was going to ask a part B. So part B is going to say how much work is done. How much work is done lifting half the chain to the top of the building. All right, I want to visualize this situation as well. So here's my building that I have here, right? And I'm not going to draw my stick figure anymore. All right, so I have my chain hanging. It's 100 feet. Now I'm only moving 50 feet. I'm only moving 50 feet. So let me pick a different color. I'm only moving here. So if I'm my little stick figure dude, as I pull the chain, I'm going to stop at this 50-foot mark. Excuse me. And when I stop, the remaining section of this chain, I'm going to switch to green, or red I meant, the remaining section of the chain still hangs below me. So if I take the first 50 feet and pull it up, what I'm left with is holding the last 50 feet of the chain. All right, so how I'm going to handle this situation, I'm going to stay in the color red. Actually, I'm going to switch back to blue. So this first 50 feet of chain, the work done is the variable 2 pounds per feet. And I'm only moving that variable weight over the first 50 feet of motion. So the way that we're going to deal with the second segment here is we're going to treat this as just like a box hanging on the end of this chain. So this chunk of chain on the bottom half doesn't lessen, if you will. So if I just had like a big huge box tied to the bottom at the 50 mark of this chain, this is like a big constant piece of weight moving. So what I'm going to do then is switch to red, and what I'm going to add really is the force times the distance associated with that bottom half of the chain. So the force of that bottom half of the chain is the 2 pounds per feet times the 50 feet that hangs there. And then I have the distance that moves is the 50 feet. So this chunk of chain, again, if I'm thinking of this as just one heavy piece of weight here, all the chain is gathered together, it moved 50 feet. So it stopped here. It moved 50 feet. So the distance that it moved was 50 feet. The weight of that chain was the 2 pounds per feet times the 50 feet left. And we stop and think about this for a second, right? The chain was 200 pounds. So I moved half the chain, which was 100 pounds. So the piece of chain left was 100 pounds, right? So I have 200 pounds. I moved half, which was 100. I have the other 100 left in that case. So that's what this is giving us here. So then I'm going to evaluate this integral telling me the weight of moving the first 50 feet. So again, this is going to be x squared, and we're going to go from 0 to 50, and then we're going to add this as the the work of moving the bottom half of the chain. All right, I'm going to take out a calculator and I crunch all of this out. I'm getting 7,500 foot-pounds of work necessary to move half of the chain up to the building. So the last example I want to take a look at with you here is where we do not have a particular equation, but we have numerical data. So again, just to save a little bit of time, I did a screenshot out of Stewart's textbook. This is problem number 6 out of the exercises. The problem says that the table shows values of a force function where x is measured in meters, f of x in newtons. It says use the midpoint rule to estimate the work done by the force and moving an object from 4 to 20. So if we think of our integral formula, right, we have that the work is the integral of the force. And when we're looking at this particular problem, right, we don't have an equation for the force function, but we do have numerical data. So remember, this integral is approximated by, right, summing up all of the forces for each segment, right, times the distance that it's moved. Okay? Now in this particular case, we have specific cuts that we have within our segment. We have specific data measurements. We'll be told to use the midpoint rule. So the way that I like to think about this here is that my first segment, like an area under a curve, if you will, right? If I think about this as I have some force function from 4 to 20. So I'm integrating this force function, and so I'm going to use rectangles, right? So if I cut this into segments, I don't know if that's the right number of cuts necessary, but I'm going to think of from 4 to 8 as my first rectangle here. And so the middle value, let me switch to green, the middle value is my midpoint. So here would be my midpoint. So that gives me a rectangle that has a height of, let's say, 5.8. And the width of this rectangle is the distance between my two endpoints. So I'm going from 4 to 8, so my delta x is a distance of 4. So then if I repeat that kind of visualization of the rectangle, right, let me use this as my endpoint. So I'm going from x equals 8 to x equals 12. I'm going from 8 to 12. And then I'm using 10 as the midpoint. Here's x equals 10, and that gives me the height of that rectangle. Right, there's my 8.8, if you will. So I have length times width of each rectangle. Now, my delta x is 4 each time. Right, this one went from 4 to 8. This one goes from 8 to 12. Right, my delta x is 4 there. So I'm going to factor out my delta x. My delta x was 4. And then I'm going to sum up all of the midpoints. I'm going to switch back to green so we can see these would be the midpoints, right? Skipping, right? Left endpoint, right endpoint. Here's my midpoint, next midpoint, so on and so forth. So my first midpoint, right? My rectangle has a height of 5.8. And then my next value, midpoint is 8.8, and then my next value of my midpoint is 8.2, and then my last value is 5.2. Now remember, our units here, our delta x is our distance. We were told that that was in meters, and our force was in newtons. So we are getting meters times a sum of newtons. We're getting the Newton meters, which is the joule. And taking out a calculator, crunching that result, I get 112 joules. So that is every example that I wanted to do for you out of this section where we're discussing work. I look forward to seeing you in the next video.